So Rima Oueid, I'm a senior commercialization executive within the Department of Energy. I am completely blinded right now, so if you make funny faces at me, it's not going to make me laugh. So I just wanted to throw in a little eye candy here for you guys. Um, we're in this funny phase right now where people are asking, are there any outcomes? Is there anything that we can point to? And as some of you know, that everyone's still figuring things out. But there are little nuggets that are starting to come to fruition and at least point us in the right direction, right? Not to mention there are technologies that have been commercialized that have application today, and so we're looking at those opportunities because we want to actually show value sooner rather than later to keep momentum going within the quantum space. And what has really helped is the fact that we have a reauthorization coming up for the National Quantum Initiative Act. So there's a lot of buzz right now in DC about what should we do in the next 5 years. Well, President Biden put out a bill just last year that has encouraged the federal agencies to become quantum secure. Part of becoming quantum secure can also include having quantum technologies. So it's a double-edged sword, but nevertheless, we have introduced quantum solutions into our portfolio to be evaluated for implementation. And then we've done a number of workshops, and I'm going to go through some of these workshops where we really evaluated the opportunities and the near-term use cases for quantum. And those workshops produced reports, and they inspired a number of senators as well as Congress folks to look into the early applications, and they've produced bipartisan bills that are asking DOE in particular to apply quantum technologies on the grid and in the energy sector. So the first report that helped inspire this, and if you see the recommendations here, they map really nicely to the areas that were highlighted by the senators, Senator Cornyn and Padilla in particular. So we brought together over 100 folks, quantum experts as well as energy experts. And these were some of the top use cases. We came up with 200 use cases, but we tried to filter them down, looked at feasibility, looked at impact, and tried to balance those things. And fault prediction came up on top, energy market optimization, integrated planning and optimization for reliable, resilient grid, and then quantum chemistry and simulations. But this only looked at applications using quantum computing. So this did not look at quantum sensing, it did not look at networking and security. So we realized we had to do another workshop, and we produced another report. And this workshop was focused on not grid optimization, but grid resiliency. So we called this the Q Energy Resiliency workshop, and the report was produced. And we followed a very similar approach, brought in a lot of the same players, but more with broader scope, because we wanted to include quantum sensing experts as well as communications and security experts. And again, it was really interesting to bring these two worlds together, or actually it was multiple worlds when you really think about it, right? Different types of experts and getting them to speak the same language. And we managed to do this in 2 days. And as a result, we also came up with additional takeaways and use cases that really, the ones that bubbled to the top. Very similar approach, measuring feasibility relative to impact. Physical grid anomalies really came up on top using quantum sensors. Contingency analysis. For those of you that might be new, we see opportunities for utilizing NIST computers to do contingency analysis, where we basically in the energy sector use heuristics. It's one of the few areas where we don't need a precise answer. We need a probability range. So NIST computers actually could play a role here. And so we see near-term application. Quantum annealing really could add a lot of value in terms of optimization. So that was in the first report. Secure communications. We see a need for this in the energy sector. The grid is critical infrastructure. We have to secure it. We have to protect it. We can use things like quantum key distribution to do that. For example, we can also, there's need for post-quantum cryptography, something that will, hopefully get us far along. And then we also are interested in new security algorithms. Again, that's PQC, and then quantum entanglement for securing our communications. And then lastly, the grid is very much dependent on GPS. GPS is easily spoofed, easily jammed, hacked, and if you can imagine where the grid is going as it is evolving, you've got all these distributed assets, solar, wind, electric vehicles, that all has to be synchronized. They all depend on GPS. But if it's jammed and spoofed, then it can create cascading effects and bring down our grid. So being able to make the synchronization, the position, navigation, and timing of our assets protected is really important here. So we see an opportunity for quantum sensing there in the near term. And just to kind of put it all together and give you something tangible to understand how this can all be utilized, I'm going to jump into a use case that I think is really interesting, that could utilize quantum communications, quantum computing, as well as quantum sensing. So V2X stands for vehicle to everything. It just means that we're able to take energy from a vehicle, put it on the home, put it in the building, put it in the microgrid, put it onto the grid. So vehicle to everything. VPP stands for virtual power plants. They're kind of serving as the orchestrator. They're the ones that take all these various devices that are connecting to the grid, and they can tell it, use less energy, use more energy, or in the case of vehicle to everything, put energy back on the grid. And they can obviously do this with solar and wind and other things. But it's a fascinating space because virtual power plant providers are already here today, and they're already tooling with your TVs, thermostats, hot water heaters, just nudging things up and down based on the load and demand that the grid has, which can be a nice sneaky way for a malicious actor to take advantage of these devices and do something malicious. So something to keep in mind, and why quantum could become a source to protect these devices. So bidirectional electric vehicles, I described essentially what it is at a high level, but most grid operators think of it as a liability to the grid. They think of it as, oh my God, the grid is going to get slammed. All these vehicles are going to just suck all the energy out, and it's going to bring these cascading effects. But there's a way we can actually design the system such that these vehicles can actually be an asset to the grid if they're bidirectional, if you put power back on the grid. A lot of people don't know this. This has been around for 10 years and more than 10 years. Japan actually had made Nissan Leafs bidirectional as a response to Fukushima. Fukushima caused their nuclear power plant, right, to come down, and that created massive energy losses. And in an aging population where people really need their electricity, that was unacceptable. And so they saw an opportunity to make electric vehicles the backup generator for those homes. And so Nissan Leafs on the road today in America are batteries essentially on wheels. And already the amount of capacity on those batteries far surpasses that of stationary storage that's connected to the grid. And when you look at the projections going forward, it's immense. Vehicles will have 10 times the amount of energy the grid will ever need. It's a powerful resource, but it can also be hijacked, right? I don't know if anyone has ever seen these demonstrations, but any vehicle with Bluetooth can be hijacked with a laptop. You could sit in the driver's seat and someone next to you or someone nearby or remote can literally hack into the vehicle and literally take control of the vehicle from you. Now imagine all these millions and millions of vehicles connected to the grid. Regardless if you make them bidirectional or not, they're going to be connected because they have to charge somehow, and they could become a vulnerability. So there's this opportunity. So there is this need for us to secure these technologies, but if we're smart, we can also optimize them. But it's very complex to be able to manage a system with that many devices on them. That essentially requires us to think about the energy grid as a two-way flow network. It starts to look a lot like these neural networks that we're thinking about developing for other types of applications. We need data and information to flow both ways. We have electrons now flowing in both directions. And by the way, we can also optimize those electrons so that we know which ones are coming from renewable sources. We can call them green electrons, and others are coming from fossil fuels. Call them brown electrons. And we want to be able to optimize for that, right? So there's all these really interesting use cases and applications and things that we can design the system to do based on what we want to prioritize. It makes the system very complex. But this is where quantum computing can come in. This is where quantum sensing can come in. And then obviously secure quantum communications. This is just highlighting, some of the challenges that the system, the energy operators are facing. We want to make sure that the energy system is designed to, we're electrifying because we're decarbonizing. We want the system to be affordable. We want to make sure that we're not making it more expensive, but then we also want it to be reliable and resiliency. So these are all the variables that we're trying to manage and balance. And in some cases, there are trade-offs, but there are sweet spots, and that's what we're aiming for. So as I kind of gave you this overview, it shows you the potential application here, the potential applications here that quantum computing, quantum sensing, and quantum networking and communications provide. And something else that I want to point out is there has been research done to show that we could also design quantum batteries and quantum chargers. These quantum batteries and quantum chargers would allow electric vehicles to charge in 3 seconds. That's a game changer, right? A lot of what's delayed the adoption of EVs is, well, the charging infrastructure, the time, the wait. But if it's 3 seconds now at a DC fast charging station, that's faster than what you could do today at the fuel pump. And then at home, it could reduce that to 30 seconds. So the level 2 chargers would take 30 seconds. Still better than the 4 hours that I have to wait with my vehicle at home today. There are patents already out there, and the Germans and the Japanese have already looked into this. What's lacking is a prototype, and I've looked into this. We're actually there's enough flexibility here. We could still build a prototype, and so that's something we're trying to get resources to do in the next few years. So I also wanted to highlight a recent funding opportunity announcement that we did. So after we did those workshops, we realized there's some opportunity here. We should actually start getting the labs to look into applying these quantum technologies. And so we put out a funding opportunity announcement earlier this year. And we realized that what we also need is we need a facility that allows us to test quantum technologies and empirically on energy infrastructure. So we need a user facility. And some of you may have heard of user facilities that are being proposed under the National Quantum Initiative Act, but they're focused on basic science research or they're broad. We need something that will allow us to test these quantum technologies on energy infrastructure, because as we have our own infrastructure and it doesn't behave the same way as traditional infrastructure or as the internet does, right, or as dark fiber would, because we have other options for communications. And so we find the need to actually be able to test like our algorithms in a microgrid setting and then be able to see empirically how did those algorithms actually perform. The quantum sensors also could be tested in these closed microgrids where we actually have energy infrastructure that can show us what will really, really happen. So we're not just guessing and we're not just simulating, we're actually doing and learning by doing. So we're really excited about this. Oak Ridge National Lab is looking for partners. I just wanted to highlight that. And this is just the tip of the iceberg. We didn't have formal funding for this type of program because this is on the applied side of the DOE house, not the basic science research side. And so this is just a starting point. I'm hoping that with the reauthorization, we get to do more. But nevertheless, they are interested in collaborating with folks that have great ideas. And hopefully we'll get more. And then the other thing I wanted to talk about was, in addition to the applications that we're exploring in the energy sector, we're also looking at applying quantum technologies in space. So I think last year I mentioned that we had this interest in collaborating, and now we've actually formally announced it, and DoD is a formal partner, and NASA is also a partner, and will be joining, and we're looking to actually begin space. Well, technically, we are going to start radiation testing in Q1 of 2024, and we're shooting for a launch this fall, maybe as early as September, and we'll be able to demonstrate a quantum random number generator communication from space to ground, and so we're working with folks on the ISS on that, and it's really exciting. But it's going to pave the way to do all these other things, and I think what we would like to do after that is actually put quantum sensors in space that could be utilized for imaging purposes. Now, why would DOE want to put quantum technologies in space, you may ask? Well, there's a lot of applications that we could explore. So we know that China has actually demonstrated quantum secure communications from satellite to ground, and actually was able to do some secure communications with the grid that allowed them to do it in a very robust and quick way to prevent a cascading effect. We could learn something from that. We also have opportunities to do imaging in space so that we can identify wildfires in very remote areas where there is maybe no human population, and therefore we could catch it sooner before it starts becoming costly to society and threaten human lives. We also have opportunities to do large surveillance of and be able to identify caverns underground where we can potentially store carbon or find geothermal or water sources. There's also opportunities to do siting of offshore wind, where it would be otherwise very expensive to send divers or technology. So the capability, there's a lot of opportunities here. I mentioned to you, clocks and a lot of atomic clock is basically quantum technology, right? And so we also would like to be able to help our partners navigate space. So that, NASA obviously has their purpose, and DoD has their mission space, but we see opportunities where we can actually collaborate such that we can leverage each other's resources so that we can actually do things sooner rather than later with what we have today. And then also pipeline leakage. That is something that I think is really important if we're entering a world where we're going to be transmitting new types of gases like hydrogen, which we're not really accustomed to sending through infrastructure. Being able to track and monitor that is going to be critical. So lots of great potential here, and not to mention the futuristic desire to be able to mine in space, and we might find that is going to allow us to be able to explore space deeper and further. And so I'm really excited about the future. I think that what we're trying to do here is incredibly ambitious, but we're taking baby steps along the way. But we also have a vision for that future so that we know what we're aiming for. And with that, I'm going to conclude my remarks. Thank you.